Hey everybody, so this video is going to go through the compound interest lesson. So in the last lesson we looked at simple interest, but just in general, most of the world does not use simple interest. We use compound interest. So for example, if you put money in the bank, it earns compound interest. If you take out a loan, the interest on that is compounded. Credit cards as well, everything is compound interest. So what the difference is between compound and simple interest is when we did the simple interest, the interest was just earned on the principal. So we had the principal times the interest rate times the number of years. But compound interest, you don't just earn interest on the principal, you earn interest basically on like different intervals, and you earn interest upon the interest that you've already earned. So instead of just having one lump payment of interest at the end of the loan, you earn interest at like different checkpoints along the way. And compound interest, it grows more quickly than simple interest. Okay, so here's an example of a table here. This is somebody that they put $1,000 into the bank. They have a 5% interest rate, and we're going to break down the interest that is earned every year. So in the first year, this is called compounded annually. So every year we're going to do a check-in. So after the first year, they earned $50 of interest and they ended at $1,050. But now when we go to start the new year, we're not just starting at the $1,000, we're starting with what we ended with at the end of the first year. So now we're earning 5% interest on the $1,050. And that's over for the second year. So we earned an extra $2.50 insurance. We ended at $11.0250. And then that's our starting amount here for 3 years, or sorry, for the third year. So again, we earned 5% interest on this. So we earned an extra $5.13 compared to the first year. And we end with a total of $11.5763. So we're going to use this formula here to calculate compound interest. Some of the letters that you're going to see are going to be the same. So for example, P is still my principal, R is still my interest rate, T is still my number of years. But now we have this new number here, N. And N is the number of compounding periods. So in a question, you're going to see some word that's going to say like compounded annually, compounded semi-annually, compounded quarterly, or monthly, or bi-weekly, or weekly, or daily, or it could be something completely different. But whatever the word is in the question, that is going to determine my N value. So annual is one time a year. Semi-annual means twice a year or every 6 months. Quarterly is 4 times a year or every 3 months, and so on and so on. So it's not going to tell you the N number in the question, but it's going to say one of these words that will determine the N number for you. The other difference between the simple interest and compound interest formula is this A value. And this A value is my future value. Or another way that you can think about it, it is my principal plus all of my accumulated interest. Okay, so whereas in the simple interest formula, we had I equals PRT, and we were just calculating the interest amount. When we use the compound interest formula, it's telling us the final overall amount. Okay, so that's another key difference between the two formulas. So example number 1 says Rory invests $500 at 8% per annum, so that's per year, compounded annually for 3 years. We're going to determine the future value. So I'm just going to write the formula here, 1 plus R over N to the power of N times T. And it's really important, if you're doing this calculation all in one big step on your calculator, put brackets around your exponent, your N times T. Otherwise, simplify your exponent first, because otherwise you'll just run into mistakes. So my starting amount is $500. 1 plus 8% is 0.08. Compounded annually means that N is equal to 1 to the power of 1 times 3. All right, and you can simplify this if you want to before you do the calculation, but I would just recommend writing your numbers into the formula and just punching it in as is, because it's very easy to make a mistake. To the power of bracket 1 times 3, which is just 3, and you get a future value of $629.86. So again, my answer here has numbers to 3 decimal places, but because this is a money answer, money is always written to 2 decimal places, and don't forget your $ as well. Example 2, compare the amount of interest that you earn when $1,000 is invested at 5% interest for 3 years, when it is compounded monthly, quarterly, daily, annually. So we're going to do 4 different calculations here. I'm going to write down the monthly and then I'll pause, write down the other calculations, and we'll check out the difference. So for monthly, my future value is going to be 1,000 times 1 plus 0.05 divided by, monthly there's 12 months in a year, so we're going to divide that by 12, and my exponent is going to be 12 times 3 for 3 years. So when we do this calculation, times 1 plus 0.05 divided by 12 to the power of 12 times 3, or 36 if you want to simplify it, we get 1161.47. Okay, so I would encourage you to pause the video, try the other calculations on your own, and then we'll jump back in and see the difference between the different compounding periods. So there are my 4 calculations. I've got monthly, quarterly, daily, and annually. So annually is the one that resulted in the smallest future value. Daily was the one that resulted in the highest future value. So what we can notice is the more we compound, so the more frequently we do it, I guess I can write that, the more frequently we compound, the more interest is accumulated. Okay, because keep in mind, we all started with $1,000 that we invested. So we only compounded once here. We had the least amount, the smallest future value. Then the more that we compounded, the higher the value got. Now monthly and daily, there's like just cents that are separating those. Even from annually to daily, it's just a few dollars that's separating them. But this is still an important note that the more frequently something is compounded, the more interest that it is going to accumulate. So on the next page, there are a couple of graphs here, and basically what it is saying is it's showing the difference between simple interest and compound interest. So in the graph here on the left, it's over 5 years. They're both starting with a value of $1,000, and over 5 years, the simple interest amount, the future value of it, is just a straight line going up, but the compound interest is just a little bit higher. It's curving up a little bit more. So compound interest, like we said, it grows faster than simple interest. Simple interest grows linearly, compound interest grows exponentially. Once we start zooming out even more, so now if we look at it over 30 years, we can really see the difference here where simple interest is still very flat, whereas compound interest is really taking off. And now we have a difference of thousands of dollars between simple and compound interest. All right, so just something to keep in mind. Now, example number 3 says for an investment of $1,500 at 6% per year, compounded quarterly for 5 years. Again, the key thing here that we know to use compound interest is there will be a compounded, some kind of compounding information in the question. So part A says determine the interest that is earned. So remember, when we do the compound interest formula, we are calculating the future value. We are not calculating the interest. So in this case, we're going to be doing 2 calculations to figure that out. First, we're going to figure out the future value, which I have written out right here. So we have $1,500. We're going to multiply that by 1 plus 0.06 divided by 4. Because it's compounded quarterly, so my n number is 4, to the power of 4 times 5 years. gives me a future value of $2,020.28. But we talked about in the previous lesson about how the principal plus the interest gives me the future value. So if we want to calculate the interest of something, it's the future value minus the principal. So in this case, it's going to be that 2020 and 28 cents, and we're going to subtract the $1,500 from that. So if we subtract $1,500 from our answer, we get $520.28. Now part B is asking what is the rate of return on the investment, and rate of return is something that we talked about in the previous lesson. So I'm just going to flip back here to the notes. The rate of return is the interest divided by the amount invested times 100, or I divided by P times 100. So if we go back here, the rate of return is equal to I divided by P times 100, and we times it by 100 because it is a percentage. Rate of return is a percentage. So we're going to take that 520.28 cents, divide by 1,500, and then multiply by 100. And you get a rate of return of 34.69%. And again, make sure you are rounding your answers to 2 decimal places. Example number 4. Adrienne invests her birthday money when she is 16. 12 years later, she withdraws the entire investment, which is now $2,033.75. The interest rate was 8.4% compounded quarterly, and it's asking us to find the principal. So again, I'm going to write out the formula here. 1 plus r over n to the power of n times t. Now we want to solve for what P is. We know what all of these other numbers are, so let's plug them in to where they go in the formula. 2033.75 is equal to P times 1 plus 0.084, because it's 8.4%, divided by 4, because it's compounded quarterly, to the power of 4 times 12, because it is 12 years later. So let's simplify this part here on the right first. So let's plug that into our calculator. 1 plus 0.084 divided by 4 to the power of 4 times 12 is P times 2.71166, and it keeps going forever. We want to try to keep as many decimal places as we can so that we get more of an accurate answer. And now this is just a one-step algebra equation, so we can divide both sides by this 2.71166 number, and that's going to tell us what our initial principal was. So we have 2033.75 divided by 2.71166, and we get an answer of about $750. So P was equal to 750. Example number 5 says, Trevor is 18, thinking about saving for retirement. For all of you out there, it's never too early to start thinking about saving for retirement. He invests $1,500 in an RRSP. He wants it to grow to $45,000 by the time he is 60. What interest rate compounded annually is required for his goal to be reached? So this is a kind of a difficult example to do because we need to do something called, well, we need to take not the square root, but I guess you'll see what it looks like once we get to it. So again, we can set it up using this formula here. So I'm just going to write out the compound interest formula, and let's replace it with the numbers that we know. So we want our future value to be $45,000. We are starting with $1,500. 1 plus, well, we don't know what R is, because that's what we want to solve for, the interest rate. We know that it's compounded annually, so that's just 1. To the power of 1 times, well, 18 to 60 is 42 years. So what we get here is we get 1,500 times 1 plus R to the power of 42. And now we can Simplify this a little bit. I'm just going to write the 45,000 here again. So if we divide both sides by 1,500, so 45,000 divided by 1,500 is equal to 30. And that's equal to 1 plus r to the power of 42. Now, you know how like when something is squared and you take the square root of it, it gets rid of the square? If you have something that's cubed, you can cube root it. Well, what we can do here is we can take the 42nd root is, I guess that's how we can call it. Okay, so we can take the 42nd root of both sides and figure out what our r number is. So what we get is that the 42nd root of 30 is equal to 1 plus r. And then when we subtract 1 on both sides, we get r is equal to the 42nd root of 30, and then we're going to subtract 1 from that. Now, when it comes to actually doing a question like this, there is a much easier way to do it, which we're going to talk about when we go into the next lesson. But for now, I mean, it's in this lesson, so let's do it. So the 42nd root of 30 is equal to 1.084, and when we subtract 1, we get 0.084. All right, and when we change that to a I'm going to add one more number. When we change that to a percentage, we get 8.44%. Now, like I was saying, there is a much easier way to do this. We're going to be learning how to use something called a financial calculator, but that's not going to come up until the next lesson. So I would say don't worry too much about an example like this, because there are much easier ways to solve it than doing it by hand like this. The other part of this lesson right here is called the Rule of 72, and what that is, it's an estimation of how many years it will take for an investment to double. Okay, so it's a very simple formula. The amount of years is equal to 72 divided by the annual interest rate. Okay, and I'm just going to say here, do not change to a decimal. We're just going to use the number itself. We can also rearrange the formula and calculate the interest rate that we need given the whatever number of years it is. So the interest rate is also equal to 72 divided by the number of years. So we're going to run through 4 examples here. The first one says, how long will it take for an investment to double at 4% per year? So t is just equal to 72 divided by 4. So we don't need to change it to a decimal. We don't need to add the percent symbol. It's just whatever the number is. So 72 divided by 4 is equal to 18. So it would take about 18 years. And again, the rule of 72, it's just an estimate. It's not an exact value. So it wouldn't take exactly 18 years, but it would be like in the ballpark of 18 years. Berta and Chris invested $5,000 by purchasing Canada Savings bonds. Berta's earns 8% and Chris's earns 9%. How long will each one take? Well, so for Berta would be 72 divided by 8, which is equal to 9 years. And for Chris, it would be 72 divided by 9, which is 8 years. Again, it's a very straight formula to use. Using your above calculations, your is spelled wrong, I'm just going to change that. Determine the value of Berta's investment after 9, 18, and 27 years. So we said that in 9 years it will double. So we started with $5,000, and when we double it, we times it by 2, so it's going to be worth $10,000. After 18 years, well, that's another 9-year period, so it's going to double again. So we're going to take our $10,000 and double that, and we get $20,000. And then 27 years, that's another 9-year period, so it's going to double one more time over that period, and we end up with a final value of $40,000. We have one more example here. Example 9, Abdul invests $500, doubles his money in 8 years. What would an estimate for the interest rate be? So that's just 72 divided by the number of years. So 72 divided by 8, which is 9. So his interest rate would be around 9%. So that is it for this lesson. Really the main takeaway is using the compound interest formula. Also, like I said, we're going to learn about in the next lesson how to use the financial calculator, which will really hopefully simplify some of our calculations that we are going to be doing. You can also keep in mind the rule of 72, because guaranteed there will be some kind of question on an assessment about that, but it's just 72 divided by whatever it is that we are looking for.